Today, we're going to pull back the curtain on the secret lives of your gadgets. Seriously, we're going to decode the hidden languages that all the tiny chips inside your phone, your thermostat, well, everything, use to talk to each other. By the end of this, you'll know exactly what's up with the three big ones: SPI, I2C, and UART. Let's dive in.
Okay, think about something like a smart thermostat. It seems simple, right? But inside you've got a main brain, a little sensor checking the temperature, a screen to show you what's going on, and maybe a Wi-Fi chip to talk to the internet. So how do all those different parts work together to keep your house from turning into an oven or a freezer?
Well, they're constantly chattering with each other. But it's not a language you or I would understand. They use these super efficient, specialized communication protocols. You can think of them as secret languages for electronics. The brain has to ask the sensor for the temperature. The sensor has to report back, and then the brain has to tell the display, hey, show this number.
And today we're putting the three most popular of these languages head-to-head in a, let's call it a communication bake-off. In one corner, we have SPI. In another, I2C. And our third challenger is the tried-and-true veteran, UART. Each one has its own special recipe for getting the job done.
First up in the ring is SPI. If SPI were a car, it'd be a top-fuel dragster. It's built for one thing and one thing only: raw, blistering speed.
So what is it technically? The official term is a synchronous, full duplex protocol. Now, synchronous just means all the different parts share a common clock signal. It's like a drummer keeping the entire band perfectly in time. And full duplex? That's its superpower. It means data can be sent and received at the exact same time. It's a true two-way conversation.
SPI gets all that speed by using a four-wire team. You've got MOSI and MISO, which are like dedicated one-way superhighways for data. One lane for traffic going out from the controller and another for traffic coming back in. Then there's SCK, the clock, which is that constant heartbeat. And finally SS, or slave select. That's how the main chip, the master, points to a specific peripheral and says, hey you, I'm talking to you right now.
So here's how a conversation actually happens. The master picks who it wants to talk to. Then it starts that clock signal ticking, and as it ticks, data flows out on the MOSI highway and at the exact same time flows back in on the MISO highway. This simultaneous back and forth is what makes it so incredibly fast.
So it's no surprise where SPI really shines. Anytime you need to just fire hose a ton of data from one place to another, SPI is your guy. We're talking about things like streaming graphics to a high-res color display, reading or writing to an SD card, or getting data from really fast sensors.
All right, time for our next contender, I2C. And I2C is kind of the polar opposite of SPI. If SPI is all about speed, no matter the cost, I2C is the elegant minimalist, all about simplicity and efficiency.
Now, I2C is also synchronous, so it uses that shared clock signal just like SPI. But here's the big difference. It's half duplex. That means it's more like a walkie-talkie. You can talk and then you can listen, but you can't do both at the same time. But its real claim to fame? It does its job with just two wires.
I'm serious, just two. This is the absolute superpower of I2C. You can connect a whole busload of different devices, sometimes dozens of them, to a single controller using just two of its pins. If you're designing a circuit board where every millimeter space counts, this is a total game changer.
So the two-wire dream team is SDA, the data line, and SCL, the clock line. And because every single device is sharing that one data line, it works kind of like an old-school party line telephone. Every device on the line has its own unique address, and it has to just listen quietly until it hears the master call out its specific address.
And the conversation is very polite and orderly. The master kicks things off by calling out the address of the specific device it wants. Only that device is allowed to respond, and it does so with an acknowledgement, which is like it saying, yep, I'm here and ready. Then they do their data exchange, and the master hangs up the call, freeing the line for the next conversation.
So where would you use this minimalist protocol? Well, it's absolutely perfect for any situation where you don't need earth-shattering speed. Think about checking in on a whole board full of sensors, temperature, humidity, pressure, or controlling a basic text display, or just asking a little clock chip what time it is.
And now, for our final round, let's bring out the universal veteran, UART. This one is a true classic. It's been around for what feels like forever, and that's because it's simple, it's incredibly reliable, and it just works. The keyword here is asynchronous. Unlike our first two contenders, UART doesn't bother with a shared clock wire. So, how do the two devices stay in sync? It's actually pretty clever.
They just agree on the timing, the speed, which is called the baud rate, before they even start talking. It's like two musicians agreeing to play a song at exactly 120 beats per minute without needing a conductor.
UART communication is beautifully direct. It's a simple point-to-point connection with just two wires, a transmit line, or TX, and a receive line, or RX. The TX of one chip connects to the RX of the other, and vice versa. And that's it. You've got a direct, two-way highway for data to flow.
Now, since there's no clock, the timing is handled by wrapping the data in a neat little package. The line is normally just sitting idle. To kick off a message, the sending device sends a start bit. That's the signal for the receiver to start its internal stopwatch and begin listening at that pre-arranged speed. After the data bits go through, a stop bit signals the end of the package, and everything resets for the next one.
UART is a real workhorse. This is the protocol that powered the old-school serial ports on computers for decades. You'll find it absolutely everywhere, talking to GPS modules, inside heavy industrial machines, and when you pair it with other standards, it can even handle reliable communication over much, much longer distances than SPI or I2C could ever dream of.
Okay, the stage is set. We've met our three contenders, the Speed Demon, the Minimalist, and the Universal Veteran. Now it's time for the final showdown. When you're building something, how do you actually choose which champion to use?
Well, it almost always comes down to this one central trade-off. On one side, you have pure, raw speed and performance. On the other side, you have wiring simplicity and the ability to connect lots of devices. Are you trying to move a ton of data really, really fast, or are you trying to connect a dozen different parts using the absolute minimum number of wires?
And this table really lays it all out. When it comes to speed, SPI is the undisputed champion. It's not even close. But look at the wires category. I2C is the master of efficiency with just two. Then you've got duplex. Can they talk and listen at the same time? SPI and UART can, but I2C can't. And finally, error checking. I2C and UART have some basic error detection built right in, which is a nice little bonus.
So what's the verdict? The truth is, there is no single winner. The champion is whoever is right for the job at hand. You choose SPI when every single microsecond counts, like for a video display. You choose I2C when your board is crowded and you need to talk to a whole ecosystem of different sensors. And you choose UART when you just need a simple, rock-solid, no-fuss connection between point A and point B.
So there you have it. The secret languages of your gadgets aren't so secret anymore. You know the Speed Demon, you know the Minimalist, and you know the Veteran. The only question left is, for your next brilliant idea, for the next thing you build, what secret language is it going to speak?